Hi, everyone. Um, Zoom is still letting people in uh, from the waiting room, so I'll wait just a moment until the numbers seem like they're stabilizing. Hello. Okay, so I'm going to put a link in the chat to the slide deck that I'm using, which includes in the repository a link to a hosted version of the slides that I'll be going over today. So hello again, everybody. It's great to be with you today. I'm happy to be here. I was hoping to be in person for this year's conference, but it didn't end up working out. So I'm glad that this format was available so that I could participate still. So this is really wonderful. So thanks to the organizers for setting this up, and welcome to this tutorial on causal inference in R. And so this is going to be a presentation. Causal inference is a nuanced topic. I feel, learning new things every day about it. And so, of course, you can't learn causal inference as a whole in an hour. And so instead, what I'm going to focus on is one particular example with one particular set of techniques that are emblematic of the workflow that you need when you're trying to make inferences about causality from data, which is a very tricky topic, very, very challenging indeed. So, causal inference in R is also the name of a book that we're writing, Causal Inference R, and really a set of efforts that we've had around education for causal inference and a set of tools to enhance the ecosystem for causal inference in R. You can find our book at r-causal.org. It's a work in progress, and so you'll see that some chapters are in a completed state, and some chapters are in more of a placeholder state. So we're actively working on it. We're hoping that this year will be our last year with the first edition, and that we'll have something ready by the end of the year. But many of the topics that I'm going to talk about today, you can find resources in our book and many other great books for exploring those topics in more depth. So I mentioned that we're going to be covering in this tutorial a workflow for causal inference. And so this is really a sort of a truncated version, a very simplified version about some of the main points that we think are particularly important. I'll point you to our book for more nuanced take on a lot of the other details of the causal workflow. But these are some of the really big ones that we think are really important. The first one is the absolute single hardest one of the whole workflow. And whenever you encounter something of an educational resource like our book or like this tutorial, usually people will just hand you this one, which is to specify a causal question. Of course, people have no trouble specifying research questions. There's lots of scientific papers out there, but specifying a good question is very challenging, a good research question in general. And then specifying a good causal question also comes with its own nuances in terms of trying to be clear about what it is that you're trying to do, what it is that you're trying to answer. Causal inference comes with a lot of assumptions in data that's not randomized. A lot of those assumptions are we have no reason to believe that they're correct, and so we have to be very clear about what the assumptions are that we're making. And so we're going to use a particular technique called causal diagrams to draw some of those assumptions. We're then going to model our assumptions. There's a million different types of models out there in the world and many ways of applying them in causal inference. We're going to be using one particular model today called an inverse probability weighted model. It's a nice simple model. It's one of my favorites for that reason, but it's one of many types of models that you could use to answer a specific question. Just like in other types of normal statistical practice, or in machine learning building, we're gonna sort of kick the tires of our model. We're gonna diagnose potential issues, take a look at the results, like what kind of results are we seeing, and do they maybe indicate some sort of problem with the model itself. Then I often accidentally say for this number 5, then finally we're going to estimate the causal effect, because it usually takes a while before we get there. But this is actually not the final part. We're going to estimate our causal effect, but because for a lot of questions we can't really know if we've met many of the assumptions that we need to make to do causal inference, the next step is often to be doing a sensitivity analysis of our effect estimate under different conditions that we think may be feasible, that we can't look at in our data, or that we chose to look at differently in our data, and that sort of thing. So this tutorial comes from chapter 2 of our book, which covers this in a little bit more detail. And we're going to look at a research question about bed nets, which is to say the type of netting that sometimes people sleep in to keep out insects like mosquitoes, and the risk of malaria. And so I like this example a lot because I'm an epidemiologist. So if you're not super into health data, I apologize, but the general workflow really applies to any type of causal question. It just may be that there's a different type of model that's more suitable for your research question than for the type of model that we'll be using for this particular question, which will have more individual level data, household level data. So let's talk a little bit about honing this question. So first of all, I said we're going to look at does using a bed net, mosquito net, reduce the risk of malaria? But what do we mean by bed net exactly? There are many different kinds of bed nets, so many of you probably already know what I'm talking about in general, but maybe you haven't spent a lot of time in this area and you're not super familiar with what the options are. Of course, you can just use regular netting, not treated with anything. There is also now netting that is treated with insecticide, and a variety of other advances that have happened in this area. One thing that I like to point out is that in the histories by Herodotus, one of the older great examples of oral history literature, he talks about people in Egypt using their fishing nets to wrap themselves so that gnats, as he called them, won't bite them at night. And the idea being that even though fishing nets are thinner, the chemicals on them from fishing, the odor of the fish, was somehow repellent to the mosquitoes. So perhaps that's what we mean when we say bed net. So another good question about this question is risk compared to what? When we say bed net, does it reduce the risk? Reduce the risk compared to what? We can be looking at a bed net that's not treated compared to no bed net. We could be looking at an insecticide-treated bed net versus a regular bed net that's not been treated. And so we have to be very clear about what the effect that we're looking for is to hone in on a well-identified causal question. So risk as defined by what is another really good question. What do we mean by malaria risk? In this particular example, we're going to be using simulated data. And so we have access to their underlying risk, their actual underlying probability of risk, which of course we don't normally have access to. And so for this particular example, we'll be using that. But risk as defined by what, we may want to be clear in the real world, first incidence of malaria during the study period or something like that. So we want to be very clear about, what that risk actually is. And then another thing that we want to answer is risk among whom? The risk for malaria while using a bed net may be different between two different groups of people who are using it. And so we need to be clear about who that is. Again, we're using simulated data, so that question is actually somewhat easy for us. It's as Andrew Heiss, who simulated the data, referred to it as households in an unnamed country. And so we are looking at the risk of this among this particular population. So let's hone in on this a little bit. We could probably get a little bit further along with this by going back and forth. But we'll kind of stop at this point with some of the items that I was talking about. So the question now that we're going to hone in on is, does using insecticide treated bed nets compare to no nets, as in, somebody's using an insecticide treated net versus somebody who's not using a net at all? Does that decrease the risk of contracting malaria after 1 year? So this is from Andrew. And here's my favorite part. 1,700 households in an unnamed country. And notably, the data is not experimental. So this is one really important thing. One of the best tools that we have for causal inference is randomization, because it helps us alleviate the assumptions that we need to make for causal inference. And so you could imagine that at one point when we really didn't know this question, it maybe was feasible to say, hey, let's randomly give people nets or not give them nets and see how those people do over time. And that makes it really easy to do, well, maybe not easy. It makes it easier to do causal inference because we have a well-designed causal question by the nature of we know exactly what we did. That's the effect that we're doing, is the thing that we did, does that improve their risk of contracting malaria? And also it helps alleviate many of the assumptions that we need to make, such as other explanatory factors, confounders as they're called, being responsible for that relationship, and for other types of assumptions that we won't get into great detail here, but that are covered in our book. And in fact, many such randomized trials have happened over time and have given us a lot of information about this relationship. But sometimes we can't randomize. Sometimes it's unethical. For instance, today it would be unethical to withhold these nets from somebody because we know that they work. And so you couldn't do that. Other topics are not randomizable because it's not practical. Either it would take too long for the study to happen, it's just too expensive, or it's not really feasible to do a randomization process for some reason. And so we need these techniques to analyze the types of questions that we can't address through randomization, one of our greatest tools for that. So we have a small package called Causal Workshop that is mostly for getting the R packages that one needs when you're taking our workshop on this topic onto your computer. But it also contains these data that we've been talking about, which is under net data. And so this has 10 variables and as we saw before, about 1,700 households that we saw. So it includes things like whether or not they used a net, their malaria risk. Remember that we have access to this variable directly, income, health, et cetera, et cetera, et cetera. So one thing that we could do now is just say, okay, I want to know if there's a statistical relationship between net and malaria risk, and I'm going to just toss all the other variables into a regression model, which may work. Sometimes it does, and it may not. But let's take a little bit of time to do some exploratory analysis of this data. So if we look at the density of malaria risk for people who used a net and people who didn't, it does seem that people on the left here in the blue density who did use a net have a lower risk of malaria. But it could be that some of the other factors that we saw there are responsible for that using a net is related to something else that improves malaria risk. So to probe this potential issue a little bit more, we're going to use a technique called causal diagrams to draw the assumptions that we're making about the relationships between these variables. So this is a causal DAG, a directed acyclic graph. Directed because of all these arrows, they're going in one direction. Acyclic because this is not ordered from left to right in how things are happening in time, but there are no cycles here. There's nothing going around and around in a circle. And a graph, of course, because it's a graph, both mathematically and visually. And so visually, we're looking at what we think the assumptions are about these. So we've got here mosquito net use and risk of malaria. And we think that there are all these other variables that are related to these two. So we think that insecticide is causally related to risk of malaria, but because there's an arrow going into it, but there's no arrow going into mosquito net from here. So we think that insecticide resistance among the mosquito population affects the risk of malaria, but not the actual use of mosquito nets. That's what we think about this population. Similarly, we think that nighttime temperatures affect both mosquito net use and risk of malaria. Say if it's really hot, you don't want to wear your net, that affects whether or not you're using your net. But maybe it's really hot and also all the bugs are out. So that impacts your risk of malaria because there are more mosquitoes out there. So that's the type of thing that this is saying. So if we think that this is true, one really helpful thing about causal diagrams is that we can then query this diagram for a variety of things that we might want to do about our analysis. So a simple question, an important question that we want to answer is, what variables do I need to account for to correctly identify this arrow, the arrow that goes from mosquito net to risk of malaria, right? This is the one that I'm interested in. The problem is, this is the one I'm interested in here, up here in the upper left in the green. This is the true effect of using a net and its impact on malaria risk. But all of those other variables, if this causal diagram is right, all of those other variables have a structural relationship with one another and with potentially these two variables, what I'll call the exposure and the outcome, the exposure being bed net use and the outcome being malaria risk. So that's the effect that we're interested in. But if we just look at this, if we just put bed net and malaria risk into a linear regression, or we look at the mean like we were doing with the densities, what we get is a sort of a weighted average of this effect and all of these other effects. So this is a true causal effect. And these are open pathways in those relationships, which are causing an association of some sort between these two variables. And so this is the effect that we want to isolate, but unfortunately, these other pathways are polluting the estimate that we get. And so what we need to do is to find the analysis that will give us this result without any of these other results. And so a simple way that you may have heard this asked about is, what variables do I need to adjust for? And so causal diagrams have a way of telling us what the adjustment set, as it's called, is for our particular diagram that we need to do to control for these variables in order to get the true effect and none of the confounding effects. So let's move to modeling our assumptions, and I'll pause there. I'll kind of pause what I left off here about the adjustment sets, and we'll talk about that in a second when we get to our model. So given this causal diagram, we now want to create a causal model that helps us identify that true effect, that green effect in the upper left. So if you go and you use these techniques, which you can find the code a little bit more detail for getting adjustment sets in this chapter of the book and in the other chapters of the book, what it will tell us is that the three variables that we need to control for are income, health, and temperature. And controlling for them does what we would call blocking these pathways that are confounding effects. Sometimes they're called backdoor effects or backdoor pathways. And so controlling for these three variables, if that diagram is correct, controlling for these three variables will give us an unbiased effect estimate. And so we could put this into a multivariable regression model But instead, we're going to use a technique from the causal inference literature called an inverse probability weighted model. And so the first step of this is maybe something that you've heard about before, which is a propensity score model. And a propensity score model is the probability of receiving treatment or exposure or the thing that you're interested in evaluating the causal effect if it creates a causal effect. So in this case, that's net usage. So what we're building here is a probability model for net usage given the confounders that we need according to our DAG. And so those confounders are income, health, and temperature. So what we're creating here is quite literally a probability model. We're getting those probabilities, probability of net usage, conditional on income, health, and temperature. And so if we take a look at those, the first household had a probability of about 25% of using a net, 21%, 32%, 23%, and so on and so on. All right, so each individual observation, households in this data, they now have this estimate of the probability of treatment. Our goal here is not to predict treatment as accurately as possible. So if you're used to a machine learning prediction model way of thinking, this is slightly different. So we are creating a prediction model, but what we're doing is trying to reduce confounding. We're not trying to predict net usage per se. And so this is one common trip up for people, is that they'll use a type of metric to say, okay, whatever the best model is for predicting nets, that's going to be the best model to create a causal effect then, right? But that's not necessarily true. It could be, but there are a variety of reasons where that is not necessarily true. So the intention of this model is to generate probabilities based on the set of confounders that we have. And we'll talk a little bit more about what exactly that's doing in a moment. But let's do a little bit of wrangling. Let's take I like to use the Broom package for this. Of course, as we saw here, good old Basar has great ways of extracting these probabilities as it must. I like using the Broom package because it can help me work in data frames. So we're going to take that propensity score model and acquire the predictions from that model. And then we're going to calculate a type of weight, an inverse probability weight. So an inverse probability of receiving the treatment nets. And this particular weight is called an ATE weight, an average treatment effect weight. And so there are many types of effects that we can estimate from the same data with the same propensity score models. In this particular question, I'm asking about the average treatment effect among this whole population. So in causal inference, often the question that we're interested in is a counterfactual question. And so if I, for instance, am a smoker, as I once was, and I wonder to myself, if I quit smoking, will I, not get lung cancer in the future? Or if I keep smoking, will I get it or I not get it? And so that's a counterfactual question about myself. If I quit smoking, what's going to happen to me in the future? So I'm happy to say that I did quit smoking when I was 23. I'm very happy about that now, in retrospect. Wasn't very easy to do, but it was the right decision. But I now can never know the result of that other life where I kept smoking all these years, right? So now I'm going to see the result of this path, my actual life, what's going to happen. Maybe I will get it one day anyway, or maybe I won't. What I actually want to know is, it compared to that other life where I kept smoking, what's the difference in those two results? So that's the counterfactual to my factual existence. We're comparing two counterfactuals. And so the counterfactual question for the ATE, the average treatment effect, is what if all of these households received nets versus what if none of these households received nets? So we're looking at two hypothetical conditions, one where everybody got a net and one where nobody got a net. And then we're going to compare the results of those two. And so what these weights are doing is they are generating a set of numbers that we're going to use in a regression model that create what we call a pseudopopulation, where that is true, where we have two identical populations and the only difference is whether or not they got that treatment, whether or not they got a net. So we'll be able to see that a little bit better when we diagnose our model. So one thing that I'm going to want to do, if that's true, if I'm correctly using these data to estimate those two populations, if that's true, then these two populations should be more or less balanced across the propensity score. And by balanced, I mean that there's the same distribution of people along the risk, as you might call it, the probability of treatment. So we're going to use the halfmoon package and a function called geomeer histogram to look at this population level balance. So on the x-axis, we have the propensity score. So this is from that model that we made. And then on the bottom, we have a histogram of people who did not use nets and a histogram of people who did use nets across the distribution of the propensity score. So this is the distribution that we see in the raw data. So this is not too bad. There's a lot of overlap between these two groups, but the shapes of the distributions are quite different. There's many fewer people who got a net versus who didn't, and the height of the distributions seem to be at different places. And so one might ask, if just comparing those two populations, do they have enough similarity in this baseline risk, which is what we're trying to estimate, that we can make a meaningful comparison, an apples to apples comparison between these two groups. So instead, let's take a look at the pseudo population that would be created, these counterfactual populations, using the weights from the propensity scores. So this sort of like dark background here that's the original distribution that we just saw. And now these light colors that are going up, this is the new distribution for these two populations compared to each other. So now the balance for these populations is significantly better. It's not identical. You can tell that just from looking at it, that it's not identical, but the distribution is much more similar. And what little difference there was in sort of the overlap in these two distributions over the propensity scores is a bit corrected as well. And so this is what the average treatment effect weight does. It tries to create two identical counterfactual populations where the only difference here across the propensity score, the only difference is whether or not somebody received this exposure of having a net or not. So again, we're trying to make this apples to apples comparison between these two groups. And this is the type of thing that randomization does by default. It's one of the reasons that it's so great. One of many reasons is that we can assume that the distribution of baseline risk between these two populations is on average pretty good, as long as the randomization was good, as long as you have enough people. So that's the population level balance. We might also wonder about the variable level balance. And so one thing that we can do is look at the standardized mean difference between the variables that we included in our model. So I'm thinking about this because I was reading something about this today. But in randomization, sometimes what you'll see is people talking about balance among covariates being a requirement for randomization, which is not necessarily true. But it is true that we would expect that a population where these two variables are the same among the exposure groups, that the distributions would not be very different between the two of them. So we can calculate those standardized mean differences with and without weights using the tidy SMD function from halfmoon, and then plot it with this function geom_love. And so this is really just a wrapper function for creating these two lines that represent the data as we saw it, the variables as we saw it in the data, and then the variables after weighting. And this is named after statistician Thomas Love, who came up with this idea. So that's what we called it in the package, as they're often called love plots. But what we're looking at here is before we weighted this population, temperature seemed to be slightly different between the two groups, people who received nets and people who didn't receive nets. Income seemed to be considerably different, and health too seemed to be pretty different. You see there's this line here at 0.1. This is sort of a rule of thumb. People sometimes say 0.1 or 0.2. These are good rules of thumb for saying that there's a meaningful difference statistically between the groups. Rules of thumb are just rules of thumbs. We don't put a lot of weight, excuse the pun, a lot of weight onto those personally, but it's a way of thinking about it that represents the amount of difference. The larger point here, though, is that before we reweighted this population, there were differences between these variables and among those who used nets and among those who didn't. After weighting, those differences are almost completely gone. And so that is what we were kind of hoping for. It's not guaranteed, but it does make us feel a little bit better that happens. So let's now take those weights and apply them to our model to estimate the causal effect. So the outcome model, we now have a data frame, by the way, that has the original data in it, as well as these weights that we estimated, which the variable name in this data set is called weights. The outcome model is actually pleasantly simple. It's a marginal linear regression model because malaria risk is a continuous variable. And we've got net on the right-hand side. That's the variable we're interested in. So remember, in these two populations, there should be no other factors that are contributing to the relationship between these two. Ideally, we would have closed all of those confounding effects and now just have the true effect, whatever it is. And so we can make this just simple marginal estimation in the weighted population because that's what we're interested in, is this difference in the pseudopopulation where everything is the same except for whether or not you received weights. And by everything, I mean the everything that we specified, which is the set of confounders. Unfortunately, this is not guaranteed to work on variables that we did not include in our model. So don't get your hopes up if that's what you thought. So if we fit this, the relationship that we get here is that for people who used nets, we have the intercept and the net true, which represents whether or not you used a net. So for people who used a net, the risk of malaria is about negative 12.5. And so these are sort of unitless measures of risk. This is just from the way it was simulated. But that's the difference, is that when you use a net, it reduces your risk by this amount. So our LM model is very simple. We've just got these two variables in it, our data, and then the weights that we calculated. We do have a little bit of a problem, though, which is that hopefully this effect estimate is right. We've got our fingers crossed that we've got everything correct up until this point. So hopefully this point estimate is correct. But these confidence intervals, the standard errors from the linear regression model, are treating these weights as if they're frequency weights, something that you might see in a survey population or the like, where those weights are fixed. Those weights are real. But as we know, we just calculated these weights. And so there's some uncertainty to the process of calculating these weights. And so these confidence intervals are not quite correct because they don't account for the uncertainty of the modeling process of the counterfactual population. So there actually is a closed form solution to this for propensity scores, but for a lot of causal inference problems, there's not. And so often you'll need to bootstrap the entire causal modeling process in order to get that answer. And so here I've got an example of fit IPW, inverse probability weighting, not quite rightly. So first I'm going to use the bootstrap from our sample from the tidy models ecosystem. Of course, you can use boot or any other tool that you like for bootstrapping. It's not relevant, but I like our sample a lot. And so this analysis function is getting the bootstrap data set. By the way, excuse me if you don't know what bootstrapping is. It's a way of resampling data that allows you to make uncertainty estimates when we don't necessarily have a closed form solution for the standard error. So there's a little bit more detail about that in our book. So what you might be tempted to do is to fit this model LM with the weights that we fit. But this modeling process, again, does not quite capture the uncertainty that we have. So it's going to treat these weights as the same across all the bootstrap populations, which it's not. And so actually, we need to do the entire fitting process. We need to fit the propensity score model, calculate the weights, and then use those weights within each bootstrap sample. So for the R sample package, they've got this great function bootstraps, which will create 1,000 copies of your data set and put it in a list. And then we can apply those copies to the data to the function that we just wrote. So for instance, if we take the first instance and use the function fit ITPW that we just wrote on the first item of this list, the result that we get back is not there for some reason. Excuse me. I expected the result of this to be seen. But I think what I was actually intending here, now that I think about it, because I have this n written here, what it's doing is it's fitting those on n bootstrap samples, where n is the number in this object. Okay, and so this is the result that bootstraps give us, and then we can apply this function to each of those bootstrap data sets. So this gives us something like this. So we have the splits. Those are the bootstrap samples. We have the ID. That's just an ID variable. But now we also have this boot fits object. So what I did was I mapped all of those bootstrap data sets to the fit IPW function in order to calculate that. And so, so the results that you would have seen if I had read my slides correctly, the results that we would have seen if you had done splits with n as 1 here, the result would have been this. So this is the results that we would see for net true for the first bootstrap data set in our population. And so we end up getting 1,000 of these results because that's how many bootstrap estimates we wanted. And if we go through and we pull out all of those estimates, we then end up with a distribution of estimates that more accurately represents the uncertainty here. So you should more or less be getting the same results. Excuse me, I see a couple of things in the Q&A. Oh, I can't see the Q&A. Let me stop sharing for a second.
So we have a question from Madeline.
Yes, I see it.
Yeah, okay.
Yeah, so sorry, Madeline, I didn't see this earlier. Are you modeling risk per family unit or per individual? In this simulated data, the unit of analysis is family unit, is household, and not per individual. But propensity scores apply equally to any unit of analysis. So it could be, you could be doing it on the individual level or on the country level or whatever your unit of analysis is. And so the idea extends neatly to all of them. Okay, and then could I explain the difference between using potential confounders as weight compared to just adding them to the LM formula directly? This is a super good question. There's a bit of a nuanced answer to that, but let me pull my slides back up. Okay, let me go back here and just kind of highlight what it is that we're doing here. So the question is about this sort of two-phase modeling process, which is first we fit the propensity score and then calculate the weights, and then we apply the weights to the LM model. But couldn't we have just put these three variables into this model? And the answer is sometimes. Technically, the result that you get is different statistically, because the result that you get from the IPW result is the marginal association between the two. Whereas if you just put the variables into the LM formula, what you get is a conditional relationship. So net conditional on income, health, and temperature. An interesting thing about IPW is that when we fit this, what we get is the marginal relationship. So that's the type of relationship that you would see just by doing a simple comparison of distributions rather than any other type of conditioning. And that's because effectively what we're doing is comparing the means in the two pseudopopulations, where these three values have been balanced. So that's one perspective on why might you want to use propensity score versus LM. Maybe you do want a conditional effect. That's fine too. Sometimes that's useful. The other answer is that you don't always know. It's not always super clear what the conditional outcome regression, as it's sometimes called, because you're regressing on the outcome, the malaria risk. It's not always clear what the estimand is. And I kind of skipped over this idea, but this is really what we're trying to estimate in the causal question. We have a really good chapter on this written by my co-author, Lucy, in our book about causal estimands. One nice thing about causal methods is they allow you to be extremely precise about the estimand that you're trying to estimate with your analysis. With a conditional outcome regression model, sometimes the result overlaps with the ATE, and sometimes it doesn't. There are other sort of quirky things about that. That being said, for a lot of simple problems like this, you're going to get the same answer because they're similar enough that they reduce to the same problem. There are more complicated analyses, particularly analyses that involve looking at an exposure over time, where there's sort of a feedback between the confounders and then the effect that you're looking at, where these methods actually just don't work using LM and the like. And so that's a more complicated topic that we're working on now for our book. So it's kind of fresh on my mind, but I don't have great resources to point you to yet on that topic. So for a lot of problems, it's going to be fine to just use an outcome regression. You can be clearer with the causal modeling approach as to what it is you're trying to estimate. And for some classes of problems, you can only estimate them with things like inverse probability weighting and other types of models. Okay, I have to stop sharing my screen again here because I can't see the Q&A. Okay. Yeah, so the magnitude of the risk, how do we interpret that? So in some sense, it's not really interpretable because we don't know what those units are of risk. They were just calculated. They represent a scale of 0 to 100, where 0 is no risk and 100 is absolute risk. So it's sort of a expansion of a probability scale. Although I don't know if when Andrew simulated it, if it maps directly to that. But because this is a linear regression, it's not a multiplicative relationship. It's an additive relationship, which is to say that when we see an estimate of negative 12.5, we say that the risk is 12.5 units lower, whatever those units are of that particular scale. Right? So if you think of those units as being just the probability times 100, then it would be 12.5% lower. Okay. All right. So let's keep going. I can answer other questions in a moment once we kind of work our way through this. So we can also calculate confidence intervals from this distribution. So now we have more accurate confidence intervals about this estimate. So the lower confidence interval, 95% confidence interval, is 13.5, negative 13.5, and then the upper is negative 11.6. And so in this particular example, this won't always be true. It's usually true. In this particular example, the confidence intervals are a little bit wider because we have that element of uncertainty about modeling the propensity score. So one thing that why I'm pausing on questions that I really want to get to is one of my favorite things about this roadmap for answering causal questions, which is conducting a sensitivity analysis on the effect estimate. And the reason that I like this so much is that often when people are talking about results from observational data analyses, they say, well, you don't really know if you've controlled for all the variables that you need to control for. There might be some unmeasured confounder out there that is responsible for what you're seeing. And that's an important question. Often you hear it, though, as just sort of a brick through a glass window. People aren't thinking about what does that mean, actually. And there exists a whole class of techniques for probing our results under different conditions. And so we're going to look at one of those things that we can do. So let's consider for a moment that there's another variable out there that is not in the causal diagram that I presented to you at the beginning of this tutorial, which is a genetic resistance to malaria. And this actually does exist. There are people in the world that have this, and there's one particular ethnicity in Africa that has a really strong genetic resistance to malaria. So consider this hypothetical situation about our data. People with this genetic resistance have, on average, a lower malaria risk of about 10. So about negative 10 is their relationship with it. And about 26% of people who use nets have this genetic resistance. So this is about genetic resistance. It doesn't tell you anything about using nets, but perhaps there's some sort of historical circumstance where people who have this genetic resistance also happen to have been, the beneficiaries of nets in the past, and it's just a common thing in this particular population. Whereas people who don't have nets in our population, who don't use nets, in our population, have a genetic resistance in about 5% of those people. So to say that again, this genetic resistance lowers risk of malaria by about 10. And about 26 people who use nets have it, and about 5% of people who don't use nets have it. So there's this relationship between both of those variables. So we're going to use an approach called tipping point analysis. And this is a package from my colleague Lucy. And so this is a package called tipr. And one of the functions that it has is adjust coefficient with a binary confounder. And so if we have a binary confounder that we have information about, but that we don't have in our data, all is not lost with it, we can then take that data and see what the effect would have been if we had applied that confounder to our analysis. And so I plugged in those numbers, the prevalence of the binary confounder among the exposed people who use nets, the prevalence among people who don't use nets, and then the relationship with the outcome, which is malaria risk. And so the result that we get here, so we have the effect observed and the effect adjusted. So 12.5 is what we got before. And then negative 10.4 is what we got after we used a tipping point analysis to see what the adjusted effect would have been had we had that data. And then we also have the same thing for the confidence intervals, which is a handy feature of tipr. So that's good news, because actually the DAG that I showed you before was wrong, which is a risk in the analysis that we're making. This requires a great deal of domain knowledge to do this well, and it's still very difficult even if you have that. So what is new about this graph is this variable down here, malaria resistance, that has an arrow going into risk of malaria and an arrow going into mosquito net. So that's that relationship that I just showed you. And that is this DAG presented here is the actual data generating mechanism for the simulated data set. And so when we see 12.5, we know that that's not right, because that's not how the data were simulated. And in fact, the true relationship from the data generating mechanism was about negative 10. So the result would have been negative 10 if we had fit the correct model to begin with. And so in this particular case, the adjustment actually worked extraordinarily well in terms of dealing with the confounder that we didn't have measured. Another type of thing that I won't cover here, but is covered in our book, is unmeasured unknown confounders. What if there were confounders that we don't even know what they are? We don't have any information about them. We don't know their properties. We don't even know what their names are. And so we can probe that too. How many confounders would there have to be? What would the strength of the relationship between a confounder that we don't have measured have to be to change our decision about the results of our analysis? So this is why this is sometimes called tipping point analysis, because people will often say, what what would have tipped the result to 0? How bad would confounding have to be to say that actually this is a null result or in the wrong direction or whatever? So I'm reaching the end here, and then I will go back to the Q&A board. But let me kind of just review what we've done here. So we talked about this roadmap of sorts of a causal workflow. And again, this is sort of a simplified version, but these are some of the main points that you see in most causal analyses. So the ones that are really glossed over are the two hardest, which is specifying a causal question, getting that accurate and honing that question. It can be very difficult. And even more difficult is correctly drawing the causal network of relationships that we have. As we saw before, even one misspecified relationship can have an impact on your results. You know, we got everything else right here except for this one relationship, and that distorted our effect. So it wasn't by too much, but it did distort our effect. So this is a very challenging thing to do and requires a lot of thought. So we modeled our assumptions. In this particular example, we used inverse probability weighting, IPW model. We diagnosed our models. We looked at the balance as something that we would expect as the result of these models at the population level and then at the variable level. Then we took our weights and we plugged them into a simple regression model to estimate the causal effect. We did have to do a little bit of tweaking for our workflow there to get the correct standard errors so that we're not being overconfident in our result. But this last step statistically was not very difficult. But then that's usually not really the last step, because often we need to go back to these stages and say, what if I was wrong about something? What if I misspecified something? There exists a whole set of tools for probing that result that are really critical to probing causal inferences when you're not dealing with randomized data and when you're dealing with randomized data, but you don't have to do some of the same things that you do with observational data. And so tipping point analysis is just one of those examples. It's a great one because it deals with unmeasured confounding, which is one of the things people like to talk about most. But there exist many other types as well. And as a reminder, you can find this particular analysis in greater written detail in the second chapter of our book, as well as a lot of other topics, different types of modeling, a more nuanced view into this causal workflow, and some of the issues that I brought up, like more sensitivity analyses, dealing with DAGs, making DAGs, like what's a practical workflow for making those causal diagrams, and so on. And so before I go check the Q&A again, I just want to say thank you to the R Consortium who's been supporting our work on this, and to my co-authors and co-developers, Lucy D'Agostino-McGowan and Travis Gerke, without whom a lot of this work I wouldn't have been able to do. And so I'm very grateful to their contributions to this as well. And so thanks to all of them. And then let me check. Okay, let me check the chat here. How much data is needed for causal analysis? Okay, and then how would this framework differ for retrospective data that is not necessarily, share the link. So let me do this again. So I'll share a link to these slides, and then I will also share a link to our book, and then I will answer the questions that have been posed so far. Yes, okay, great. So I think I got everything in the chat. So now the open Q&A questions. So how much data is needed for causal analysis? This is sort of orthogonal to causal analysis. It's the same problem as any other type of statistical problem. You need as much data as you need to correctly calculate the effect with the amount of precision that you want to calculate it with. And so in that sense, it's the same type of power analysis that you might need to do for any other type of statistical problem. Simulations can be really useful for doing power analyses, sample size analyses for causal inference, because often they're so complicated that a closed form formula doesn't exist for, how many people do I need? So there is no good number. as with all data, more is better, but it depends on what types of models are using, what's the effect size, and et cetera, et cetera. So with this, how would this framework differ for retrospective data that is not necessarily randomized? So, so the example that I show is not randomized. So it depends on really what you mean in retrospective. So this framework is I would say more complicated for non-randomized data. That's the framework I just showed you. The ideas are identical to randomized trial. It's just that we know that some of the assumptions that we have to make in randomized situations hold some of the assumptions that we need to make. And so that's the beauty of randomization, is that we don't have to do the worrying that we need to do with observational data that has not been randomized. So retrospective, it depends on what you mean by that. If you're collecting data, if by retrospective you mean you're starting data collection today, and you're going in the past and asking people about things that happened in the past, or you're collecting data about things that happened in the past, then really your fundamental question is, are you getting data that matches the actual causal structure of your question? One of the things that can happen is that something happens after, and people will it will affect the data generating mechanism for your study. So somebody who is sick and is thinking about the things that they were exposed to that might have made them sick has been thinking about it a little bit more. Somebody who's not sick in your study hasn't thought about it as much, and maybe is not thinking about it as much and not giving you as accurate as an answer. So you have other types of issues that are related that we do talk about a little bit in the book. But the randomization process is not required for what I just saw. It's just extraordinarily helpful. All right, what are the advantages and disadvantages of using propensity scores in comparison to regular regression analysis without the weights? Yeah, so that's the answer to that is the same one that I said before. The advantages to propensity score analysis in this case is that, one, you get a marginal effect. Maybe that's the effect that you're interested in. And two, you can be more precise about the estimand that you're estimating. So we estimated the average treatment effect, but there are other estimands. The average treatment effect among the treated, the average treatment effect among the untreated. These go by different names in different fields. And with weights, you can reweight the population in different ways to get those estimands directly that are a little bit more complicated in multivariable regression, as you saw. The upside to multivariable regression is that people are more familiar with it. So sometimes if you're going to get the same answer, sometimes it's better to report the simpler method that people are not going to mentally struggle with. The other reason that you might want to use linear regression or any other type of regular regression is that you don't want a marginal effect. You want a conditional effect. Sometimes that's what people want. And of course, I will say again that this is just one type of causal modeling process using the propensity score. There are other approaches. G computation is one of my favorites. There's also methods that don't that use different types of data or different types of assumptions, difference in difference, regression discontinuity, and many other types of modeling. So this is just one. Okay, let me reframe. Can one even analyze a causal effect if we can't be sure about the data, how the data were randomized, e.g. clinical data where we have limited information on how treatment was assigned to individuals? I thought one would call it, rather call it correlation or association at this point, and not causality, if that makes sense. It does make sense. And so that's why you need to go through the process of clarifying your not just your question, but your assumptions around your question. So that relates very critically to the first part of your question, which is how treatment was assigned to individuals. Can we predict that accurately as it relates to the outcome as well? So that's an important part. It doesn't need to perfectly predict treatment assignment. It needs to predict it for all the confounding pathways. So the question of can we be sure about that is a question of is a question for you to probe. What do you think that those assumptions are? Can you sit down and specify what you think those relationships are? Do you have the data to do that? If you don't have all of the data, is there a subset of the data that can accurately answer the same question? And so that's one of the things those DAGs are really useful for, is that you can query that for many adjustment sets. So sometimes there's an adjustment set for variables that you have, and another one that you're missing one or many variables. In theory, if your DAG is right, you can still estimate it with those missing variables, as long as there exists at least one valid adjustment set that you have data for, and your DAG is right. That part is very important. So I had another thought about that. So, oh yes, and so then if you're concerned that maybe you don't have all those data, then you need to do sensitivity analysis and see what the fallout of that is, that relationship. In terms of calling it correlation or association and not causality, that's how I was trained too. And I don't do that anymore. The reason is that I'm not trying to estimate correlation. I'm not trying to estimate association. I am trying to estimate causality, and I want to be clear about that. Whether or not I have accurately done it is a different question. But when I say I'm estimating a causal effect, I mean I'm trying to estimate a causal effect, right? And so then the answer for you to answer as a researcher is, did I get there? Did I succeed? Is it reasonable to assume that I've dealt with all of the potential problems, all the potential confounders, and other types of problems that come up with observational data? So there's some interesting topics on that, but it may just be correlation. You're right. It may just be correlation, but that's not what we're trying to estimate. Great. Yes, we are going to publish our book in a physical version. So one day. I know I appreciate it when people ask me that, because I often like to have a book in my hand too. That's why I've got all these back here, even though half of these books are available online. So my apologies to the trees that I've ruined from all the paper, but it feels better to me too. Okay, I think I've got them all. So our book is available, and if you have any questions about anything, feel free to contact us, and we'd be happy to talk further about anything. So thank you for coming. It's great to share this work with you, and we hope to have a completed version of our book to show you soon. Thank you.